Well, thank you. I'm very excited to be here to tell you about the work that my group has been doing at MIT for the last 20 years now. I'm going to tell you about something called quantum magic and nanocrystals. Quantum dots are where the quantum magic happens. Quantum dots are nanometer-sized crystals of semiconductors. They're tiny, tiny crystals. They're made of thousands or hundreds of atoms, so they're bigger than an atom, they're bigger than a molecule, but they're still really tiny. And they have some very unusual properties that I'll be talking to you about today. Let's start by having a picture of what a quantum dot really looks like. Now, we can't use a regular microscope to see a quantum dot because they're way too small. You can't use a light microscope. So in order to see them, to know that we've actually made them, we have to use an electron microscope. And this is one of my students working on the electron microscope at MIT. And this is what comes out of the electron microscope. It's a little picture where each one of these little particles, these little crystals, is just a few nanometers in size. Let's start with something really huge to get an idea of scale. Something really huge, like the sun. The sun is 1 billion meters in size. Now, humans invented the meter because it's on the human scale, right? We like to measure things that are on the scale of a human. And I brought a meter with me. Come on up. There's a meter right here. Mia here is 1.25 meters tall. It's a great frame of reference. Now, compared to the sun, she's a lot smaller, right? So the sun is huge. In fact, the sun is 1 billion times bigger than Mia here. If I were a quantum dot, I would be tiny compared to Mia. In fact, a nanometer is 1 billion times smaller than a meter. So the quantum dot would be 1 billion times smaller than Mia here. The quantum dot, Mia would be like the sun to a quantum dot, to give you an idea of scale. Okay? Thanks, Mia. Okay, so now we have an idea of scale. They're really tiny. They're bigger than atoms and molecules. They're still so small you can't see them in a microscope. They're as small as the sun is big to us. How do we make them? What you see here is our pot. This is where we do our cooking. The temperature is about 500 degrees Fahrenheit, 300 degrees Celsius. Okay, so you're going to see the movie of this being made now. So there's the chemicals in the syringe here that are going to make the quantum dots. This is at 570 degrees Fahrenheit. And you see the color of the quantum dots is red now. And as it's cooking, the color is changing. It's going to get darker and darker. They're getting redder and redder as the particles get bigger and bigger. And when they're diluted in a solvent here, you can see that they're different colors. And it's even more impressive than looking at them with visible light is to look at them under UV light. So we shine ultraviolet light on them. The big particles on your right here, the red ones, are bigger than the ones on the green ones that we're taking out of the pot a little later. Okay, so there's a size difference here. It's the same material. It's the same semiconductor. The only thing that's been different is the size of the particle. 1 nanometer for the green ones, 4 nanometers for the ones that emit red. Why is that? Why is that? Well, you know other places around you where size makes a difference. For instance, when you're talking about acoustic waves. If I take a flute and I take a piccolo, they sound different. The flute sounds deeper than the piccolo. Why is that? It's because the sound wave that fits in a flute is longer than the sound wave that fits in the piccolo. The shorter the sound wave, the higher pitch you have. We also know that from organ pipes. You have the big organ pipes that can fit a big sound wave in them. They're deeper sound, lower pitch than the narrow, teeny organ pipes that are shriller. We also know that with strings. If I take a stringed instrument like this ukulele here, and I make the string shorter, the sound is a little higher pitched. Okay, what does that have to do with quantum dots? All this is the human scale. Well, it has to do with the electrons that are in quantum dots. When you think of electrons, you usually think of particles that are going through wires, powering your power tools, your chip, or whatever, little particles of charge. But if you take that little particle of charge, that electron, and you try to stuff it in a little box that's a nanobox in the size of a nanometer, it changes its properties. It becomes like a wave. It fills up that box like a wave fills up a flute or an organ pipe. This is quantum magic. This is this funny world where things don't behave the way that you expect them to behave. All right, so now I've got my boxes and I've got some electrons in there, but just like the strings on the ukulele don't sing by themselves, I have to do something to the flute to get it to emit a sound. I have to strike the particle somehow to get those electrons to behave like waves and for the energy to come out as light. Okay? So for the ukulele, I pluck it. That's how I create the sound. For the electrons, to get them to be waves, I strike them with light. I can strike them with a blue photon, or blue light, or UV light, and that creates those electrons. They become waves, and they start to emit the light. So now you know why they work. You know about the magic of quantum mechanics that makes them have different colors. And they're really little pieces of rock, so they're kind of stable. So it took us about 15 years to go through some really fundamental research to get to where we are in terms of understanding all this stuff. And about 10 years ago, we realized that if you have something that's bright, that's tiny, and that's colorful, they could also be useful. And I'm going to tell you about two uses of the particles, one in biology and one in electronics or lighting. Let's start with the biology. It turns out that these particles are on the same size as big proteins. And so we can use them to image the inside of cells, for instance. So this is a cell. This happens to be a dead cell, but you can see the skeleton of the cell. These little green things are the cell skeleton. There's a nucleus, there's other parts of the cell. Quantum dots of different sizes have been are labeling the different parts of the cells, and you see these pretty pictures. Now, they're so bright that you can even see single quantum dots. Under a microscope, under a light microscope, even though you can't see the dots themselves because they're too small, you can see the light that comes from the dots. What you see here is a neuron that's glowing green, and the little red spots are the little quantum dots that are finding little receptors on the neurons, teaching us something about the way that electrical signals go up and down the neuron. So we can see things at the cellular scale, and we can also see things even deeper, even smaller than the cellular scale. In this case here, we were working with colleagues at the Massachusetts General Hospital, and they're interested in stem cells. They're interested in tracking certain kinds of stem cells that are connected with cancer. And those stem cells happen to exhibit two different kinds of what are called receptors on the surface of stem cells. So what we do is we can come in with two colors of dots, a red one that can find one of the receptors on the stem cell but also labels other cells, and a green one that can find, say, a third kind of cell but also labels a second receptor on the stem cell. Now we have green and red together, and that makes yellow, and then we can go inside the blood vessels of the animal from the outside, and we can watch then this yellow cell here. All the others are blue or different colors, and there's the bone here, there's a blood vessel, and we can track the stem cells as it goes around, and so we want to find out what the environment is of that stem cell in real time. Okay, so quantum dots were great in terms of imaging things, but it would be great to make them even smarter. So again, this is working with colleagues at the Massachusetts General Hospital, and they're interested in curing cancer. They're interested in delivering drugs deep into tumors. And the biggest problem we have with cancer right now is that it's very hard to get the drugs to go deep into a tumor to kill the cancer cells. So their idea was if they had a 100 nanometer particle, which is really big compared to a quantum dot, and that 100 nanometer particle was able to lodge itself in the tumor because the vasculature, the blood vessels next to a tumor tend to be leaky compared to normal vessels. So these 100 nanometer particles could get out, but they can't really penetrate. So if you put a drug in there, it's just going to kill the part of the tumor that's right next to the vessel. But then if you have something that can eat up that particle, like enzymes that happen to be present in the tumor, they can eat up that particle and dislodge smaller particles, and then can float around in the tumor and diffuse and deliver their payload to get rid of the cancer. That's the idea. It works great on a cartoon, but does it work in real life? First, we have to test it. Okay? And the way we test it is by having the big particle be decorated with quantum dots. And we can image the 10 nanometer particles that are supposed to carry the payload because of the fluorescence of the quantum dots. So the quantum dots are a substitute then for the therapeutic carrier. And so we do our injection, the quantum dots diffuse throughout the tumor, validating their concept. And so what they're doing now is they're actually building real drug carriers based on the size scales that we imaged here. So let me switch gears completely now. Let me go to energy and lighting. We have a big problem with energy, not because we're running out of energy, but because we're dumping all this CO2 in the atmosphere. 22% of the world's energy is spent on lighting. A lot of our lighting comes from these sorts of bulbs, these incandescent bulbs. They were invented about 100 years ago. They're really old technology. When they were invented, they were amazing. They changed civilization. They allowed people to be able to read at night, to do all sorts of things. But it's a 100-year-old technology. In fact, it's a lousy technology. In fact, they shouldn't be called light bulbs. You know what they should be called? They should be called heat bulbs, because 95% of the energy you put in there comes out as heat. Just a few percent comes out as light. They're amazingly inefficient. Okay, so we're replacing our light bulbs with these guys here, these compact fluorescent lights. I don't like them. I don't like them for many reasons. They give out lousy light. They're full of mercury. They burn out if you put them in an enclosed fixture. You can't dim them. They're just as bad as this in many ways, right? Trash. Okay. The future of lighting really is not any of those. It's light-emitting diodes. They're little pieces of semiconductor that can emit very bright light and that don't burn out. And they're really tiny. And they're at least 10 times more efficient than incandescent, and they're getting more and more efficient. There's a problem, though. Everybody wants to be like outside in the sun, and that's why we like incandescent, because the colors that come out of incandescent cover the visible. You have nice red. You look great under incandescent lights. LEDs, like the kinds that you can buy at CVS, if you shine light on yourself, you look kind of pale, like a ghost. And you don't want to use that in your bathroom, right? Because it's missing the red. But quantum dots, because we can tune them to have very sharp colors, can be used to add back the red to LEDs. And this is a product that's come on the market recently from a company called QD Vision that was started by a couple of MIT students. And I brought a couple lamps here, quantum dot-driven lamps. And you can't probably see it from where you are, but you're free to come up. But you can see that the normal LED light here is very bluish. If you put your hand underneath it, it's very ghostly. But if you put your hand underneath the LED light that has some quantum dots added to it to make it red, to add red, and the colors look nice. Okay, but we're not going to stop at trying to excite or strike the quantum dots to make them sing just with blue light. We can also use electricity to get those electrons to become waves inside the quantum dot. This is farther off. This is not a technology that's ready for prime time yet, but this is where we see the future going. So this is a little film where we've added a whole bunch of different size dots, different colors. Different size means different colors. And we connect it to a circuit, and it emits white light. And so now you can imagine, instead of using bulbs, tiling your ceiling or something with a film that emits white, nice, just like a window emits white light. Now, if you take the same idea and you try and put pixels, instead of having one big sheet, you have little tiny pixels, like you have in a television, then you can have a display. And this display is actually downstairs. This is a micro display. There's a dime next to it. This is a display that a gamer would want to have, for instance, with little glasses to look at the game. What's the other big problem that we have? So this is using energy more efficiently, but we'd like to get more energy also, right? So the world energy use has been going up exponentially. We're using 16 terawatts of energy, total energy use today, and let's see where we can get that energy. There are many ways to get that energy. We all like to get it from renewables: tides, geothermal, waves, hydro, biomass, wind, but those are really small compared to the amount that we use. There's one source of energy that's left that dwarfs all of these: the sun. The sun puts out 23,000 terawatts of energy. We use a small fraction. We use less than 0.1% of the sun's energy. And so that's what the future of my field is working on right now, funded a lot by the Department of Energy. We're looking at making flexible solar cells that could be roll-to-roll deposited or printed using quantum dots as the material that absorbs the light, creates these electrons, and we're trying then to harness these electrons to create energy. And this is going to require a lot of work and a lot of fundamental research. Let me finish with the take-home message. I hope that we've demystified quantum magic. Quantum magic is this thing that electrons do when you stuff them in little boxes. And if the box changes size, the wavelength of the electron changes, you get different colors out. And we can harness the power of quantum at the nanometer scale. We can harness it in biology by making little tags for imaging cells and imaging stuff going on in animals. We can use it to help us with cancer. We've harnessed it to make more efficient lighting, to go into displays, and hopefully in the future we'll be able to harness it to make better low-cost solar cells. Thank you.